Can you leave the meeting and check on YouTube?
Yeah, sure. Fine. Let me see if the camera is completely fine.
Mute this here.
Yeah. Let me see if anyone is down. Do you have internet?
What's that?
Do you have internet?
Yes,
Ah,
EDU Pro.
Yeah, you can. Sorry, do you have internet?
Yeah, I just connected the.
Okay.
Yeah, thanks so much.
So,
Funny. Kind of weird when you're juggling with all the technical stuff. Well, we seem to be good.
Just as a curiosity point, all of the students are aware not to join join computer audio at all, right?
They have no notification.
Okay.
It's only the speakers.
Okay, cool.
Yeah, if you want to participate, if you just want to watch it from remote, you have to use the live stream.
Okay. Perfect.
there is no mute. Actually, it's still sound.
Yeah, it's fine. Okay. No, it's supposed to get the sound, but you're
Yeah,
only
but
supposed to
I
get the sound on YouTube, not here.
Yeah, that's true. But I was thinking that if you like press mute, it's going to mute completely the audio, but not.
No, it's only the speakers.
Okay, it's on the speaker. Cool. Nice.
Okay, so somebody has their hand up. Okay, so good morning, everybody. We're a little bit short on staff yet, but that'll hopefully improve. I don't know why it's still showing that window. Anyway, uh, okay, so according to the schedule, we'll be starting with a tutorial in LAMMPS, rather introductory. To make it a bit more interesting to the people who already know LAMMPS, the idea is that we're actually going to show you something new. That's the LAMMPS GUI program that was essentially conceived while we're planning the last tutorial, and it wasn't ready in time, but it is ready now. Let's see, get out of there. And so I'll be starting with the show to just try and give you a bit of a tour of how this works. And for that, I first have to download it. So it's been distributed with the LAMMPS releases on GitHub. And there's one for every platform, Windows, Mac OS, Linux. The Linux version is done in a tar file with some fancy wrapper scripts, so that it should work on pretty much any Linux system that is at least as new as Ubuntu 20.04. And we need the tutorial. So you need to download the file and then just unpack it, and then you can launch the executables from the LAMMPS GUI folder directly. And you see there's a couple of tools that go with LAMMPS. And there is the LAMMPS GUI executable and the console mode regular LAMMPS executable. Those are without MPI, but OpenMP and GPU support work via OpenCL. So it should work on efficiently on many platforms, and there's no conflicts with MPI. GUI and MPI is a problem anyway, so we're just avoiding this. So we need the tutorial files, and there another URL. So unzip that one. And finally, we won't need it right now, but we need it in the next round to do some plotting. We'll create a virtual environment to have some Python tools available. And you just need to follow the commands as they're in the README file. Install all this via pip. And we need matplotlib for plotting. We need PyYAML to read YAML files, and we need pandas to manage the data. And that allows us to parse output files in YAML format without needing to write special parsers for LAMMPS files. Okay, so let's just start with the thing. So this is the LAMMPS GUI executable. Doesn't look very spectacular. In fact, it's supposed to look a bit like Notepad on Windows. It's just a plain text editor. But it has a few gimmicks that are different from other editors. So for example, it shows you the current working directory. And if I open a file, so you have the regular menus here. So if I open a file, so I go to the tutorial folder, the basic exercise, that's the first example. I open the in-friction file. Then this editor will switch the working directory to the folder where that file was found. Because typically for LAMMPS, there's other files in the same folder, like potential files, data files, and parameter settings, whatnot. So this is where it's different from a regular editor, that it always follows the current working directory of the file that you're editing. So what you're also seeing is that you have syntax highlighting, so it knows about keywords and some argument. It's not perfect, but it can help. Specifically, it can show you commands where you mistyped. Then, of course, it will not highlight it correctly, and that will help. So let me just show you the different menus. So you see the file menu is like it's typically. It has a history of files that have been opened in previous sessions, so you can quickly go back. There's, as you can see, there's hotkeys for almost any command. So if you memorize those, you don't need to use the mouse. You can actually do things directly. It has undo, redo, copy and paste like a regular editor. One important thing is we have a preferences menu where you can change settings. I'll get to that in a little bit. Then you can run the file in the input. And unlike the regular LAMMPS executable in a regular editor, it will take the contents of the buffer. You don't have to save. It will take whatever is in the buffer to execute. So it makes the process even faster. And you're not dependent on synchronization. But you also have the option to read from the file. While it's running at any time, you can stop it. It will stop at the next iteration. There is a menu to change variables. We'll get to this later. There is an option to create an image. So LAMMPS has a built-in visualizer with the dump image command. And this GUI tool has been trained to run the input to the first run, but not execute the run. Instead, just do a write dump at this point. And this way you can see an image of the initial configuration. So you see for this input, you see here the initial configuration that is being generated. There are multiple output windows that are created. So the GUI was meant to be used from a graphical environment. So typically LAMMPS output goes to a log file, goes to the screen. So you usually don't see that. You have the thermodynamic output that comes as columns of numbers. So the GUI can intercept all of that and put the log output to a window, create automatic charts from the thermodynamic data, and you can switch between them, and it's dynamically updated as the simulation is going on. And we'll just show this in a bit. And if you put a dump image command into your input where it creates regular snapshot images, it will also be detected and automatically added to a window with a slideshow. So you can basically see an animation of your simulation as it is running from the images as they are created. And you have some tools where, for example, you can get the configuration information. So this tells you which source code version was used and which packages and features are included. That's useful if you need to report bugs. There is a minimal help window giving you the minimal instructions. But then it's also set up to have an interface to launch URLs through your web browser. So you can get the how-to that is in the online documentation for the GUI, you can call it directly from the GUI window. And similarly, you can get to the top page of the LAMMPS manual. So, and it doesn't stop there. So if you're going on a command, you can do a right click and you can see multiple edit options, but specifically you can also, if you're on a keyword, if you have a command in a line, you can also directly have the documentation for that specific command open. So if you're, I mean, it's really, if you want to get people started, it's very convenient because everything is in just one executable, one program, and it will dispatch it, so you don't have to search in the documentation, which has a few thousand pages, so it's not always easy to find something. So this way, it's easy to just go back and forth. And if you have multiple possible options, let's look at hairstyle, for example. Then I can show the documentation for the pair style specifically and for the pair style command in general. It also offers some reformatting, which is also available if you hit the tab key. And if you go, let's go back to the preferences. So if you go to the preferences, for example, there are settings where you can determine how many characters you want to have the different indentation levels to work. So you can adjust this. You can turn on automatic reformatting, reindenting. And you have also automatic completion of commands. So it knows if you're typing a command and if it knows something that would fit in that place, it will have a pop-up window where it shows you possible completions. What you also can do in the preferences is can you select fonts, you can show output, and you can also determine how many processors you want to use and if you want to use an accelerator. So this always comes out at 8, but it's actually with hyperthreading, so 4 is the better choice. Okay, so now after I've loaded this input, I can run it. There's a button here, Control Enter, does the same thing. And then it will run the simulation as if you run it from the console. But as you see, it will capture the output. So you can see this in one window. It will capture, so this has a dump image, so you get a slideshow of the various images, and you can animate this. And you can even save it as a movie if FFmpeg is installed. So the precompiled packages should have an FFmpeg executable. So you have a movie that you can use. If you go to the image button like here, you will now see the end of the simulation. If you run normally, you can actually stop in between. You also see that there is a highlight here on the line number where it's actually executing. And so if we're in the middle, you get the image in the middle, and then so this is not like a regular visualization tool because it's just rerunning dump image. But you can do it with different settings. You can turn on anti-aliasing and make the make the spheres a bit smoother. And there's also a high quality output with ambient occlusion and subsurface scattering that dump image has, and then you can add here. So if you have a 3D visualization, you can also rotate in space. It's not the greatest thing, so for something really fancy, you want to use a real visualization tool, but for quick and dirty, this has the advantage that it's all built into the same executable. You don't have to switch to anything. And here you have the thermal output as graphs. So you can switch between them. There's no molecules here, so that's 0. And those data you can also export to CSV, so they can import it in Excel or similar spreadsheet programs, or you can just have data column files for XM Grace or GNU Plot. So unlike with the other tools, usually you have to have a parser that extracts this information from the log file. So this here is done in a different way, and it doesn't depend on the log file. Okay, so now let's look a little bit at the tasks we're supposed to do. So we could change the size. So I can now go to this area here, and now I have sphere that's position radius. So we can make this smaller, and Control Enter will just run it. And so you see now there is no interaction between the two asperities because they're too small. You can also change this to have a longer run. And now it will just run once and then the second time. If I do this differently, where at the end can also copy and paste, then you see here very nicely how it is highlighting the current command that's been executed. So after it's done the first run, it will jump to the next run. That's mostly useful if you have an error somewhere in the input. Let's put an illegal number there, then it will stop here and tell you the error message, and you see already the line where the error happened. So again, that's mostly made to get people started at the beginning. If people have to first learn a text editor and then also have to deal with this kind of errors, then it can be a bit demanding on the people. So the idea is with the GUI to make this a bit simpler. So now the next task is to comment out this area. And again, there's a special feature in the GUI that will make this easier. Because you can comment out the entire selection. And you can also, you can also uncomment a line or a selection. Now we have a different shape, and it will execute in the same way. So that's the first round of demos. Then you have the next. So that. Let me just stop my screen sharing. So that's now only one. And now we'll be doing some more information about it.
No, but there's no, but in the flood.
All right, I'm Stan Moore from San Diego National Labs. Unfortunately, Steve Compton was supposed to give this talk, but he's stuck in Dallas,
Well, on the.
so I'm filling it for him. Okay, so the goals for this lecture are to teach you how to read input scripts in LAMMPS, understand them. We're going to edit an existing input script, write a new input script, and then debug get an error or have a runtime problem with your input script. Okay, so what is a LAMMPS input script? It's basically a text file that contains a sequence of commands. One thing that you need to keep in mind is that LAMMPS reads the commands one at a time and executes those. It doesn't read your whole script and then run the simulation. It only runs the simulation if you put in a run command. An input script can actually run one or many LAMMPS simulations. Some commands read other flavors of LAMMPS input files, like a data file. So this could be used to initialize your simulation with the starting position, the velocities. Restart files, so if you checkpoint LAMMPS, you can restart it, as well as molecule files, which can define like angle bond topology. When the last command in the file completes, then LAMMPS exits, but earlier commands can also cause LAMMPS to exit as well. Okay, so it might help you to understand how the input script is actually parsed into multiple commands. There's a section 5.2 of the user guide for full details, so you can go look at that if you have questions. But if there's any blank lines, those get skipped. If you have a comment that starts with a pound character, those are removed. So LAMMPS will just ignore comments. If you have a really long command and you need to put it on multiple lines, you can put an ampersand character, and that will concatenate these two lines into a single command. LAMMPS then takes this line, it splits it into words by white space. So, spaces. If you need to have spaces, but you only want one word, you can encapsulate it in quotes. So like print, and then like a long string is encapsulated in quotes. Within each word, you can also have variables. So the variable name will be replaced with the value later on in your input script. So you can find a variable f as string data.myself, so that's a file name. And then you use that in a read data command. Then it will, do this substitution, and it will be like a read data myself command. You can also define variables as numbers, and then use those in other commands like fix nvt. So the first word is always the command name, and then all other words after that are the arguments. And so every single command has a doc page, and you really need to understand the command by reading the doc page. So if you have any questions, just refer to these doc pages. So how do you get to the doc pages? Well, in the LAMMPS web page at the top, there's a command section. So there's general commands and then many more, so like 110 in the current version. And then there's also the commands are broken into categories like pair styles, fixed styles, etc. And so you can click on each one of those sections, and that will show all the fixes, all the pair styles, and each one of those has their own doc page. So in the following slides, we have a command like fix, and then it has like an ID, and then a group all, and then the command name will just refer that to either a fix or fix app force. So we're gonna omit the ID and the group name. Okay, so the structure of a typical input script has several different sections. So normally the first section is global settings. So this is like setting your unit system, like SI versus other units. How many dimensions? Is it a 3D or 2D system? What kind of atom style? Is it periodic boundary conditions or non-periodic? All these have default values, which are listed in the doc page. The second step is to create a simulation box. So how big is the box? And then put in the atoms. So there's several different commands like create atoms or create them on a lattice. Or you could also read a data file or a restart file. The third step is to find groups of atoms. This is for convenience. Maybe you have multiple groups that you want to, some you want to have stationary as walls, and then others are moving. So that's how you need to define these groups of atoms. The fourth step is to set atom attributes. So this could be the velocities or the mass, the per atom or the per type mass. And then you need to define how you're going to compute your forces. So this is the pair style. So that could be like a Leonard-Jones interaction or many body potential or even a machine learning potential. And then we're gonna, step 6 is have fixed commands. This could be like time integration, like a velocity relay or constraints, maybe a thermostat or a varostat. And then step 7 is diagnostics. So these are called computes. It could be, computing energy or per atom variable or something like that. And then there's output commands in step 8. So that's like our thermal output in the log file or a dump file or a restart file. And then step 9 is an action command. So that's to tell lamps to actually run the simulation, run for 100 steps, minimize to relax the energies. And then just you can rinse and repeat and keep doing that over and over to run your simulation. Okay, so we're going to look at a specific example. It's actually the in-dot friction example that Axel just showed in the GUI. That's the two indenters moving across each other. So there's many examples of LAMMPS input scripts in the LAMMPS examples folder. You can also look at the README files to see what they do. Okay, so in this friction example, step 1 was these global settings. So it's a 2-dimensional simulation. It's both periodic and shrink wrap boundary conditions. We're just using a simple atomic atom style. We're setting some neighborless settings and defining the time step size. We're then going to create the box in the atoms. So it's the atoms are created on a lattice. We're setting different regions in the box to define, different geometric regions, and then we actually create the atoms. We also define some groups. So this is like the boundaries of the walls, and then also the high and low slabs that are moving. We also set some atom attributes. So we set some types, the mass and the velocity. And then we're defining our pair style. So again, this is how the forces are computing. So this is a Leonard-Jones pairwise potential. It has a cutoff of 2.5 Leonard-Jones units, and then just the standard sigma and epsilon of 1.0 and Leonard-Jones units. We're defining some fixes. So this is how we actually move the atoms. So we have a time integrator, time integrator. This is just the NVE, velocity relay. And then we have some other fixes that set the boundaries so that the wall atoms don't move. We have a thermostat so that the temperature of the moving atoms is reasonable. And then for any 2D simulation, we have this fixed and forced 2D, which makes sure that there's no movement in the third dimension. We also have compute. So this is computing a profile of the temperature. This is optional. This is a diagnostic. Then we have some output. So we're going to write to the log file every 1,000 steps. We're telling the log file what quantities we want, temperature, and then this Y-dim. And then we also have some dump files. So we dump an image as well as a movie. And then we finally have the action command to run the simulation for 20,000 steps. Okay, and then for the output goes to the log.lamps file. It's similar to the screen output, to standard out, but there's also some additional info. So the log file will actually echo every command, including variable substitutions, which is useful for debugging. It contains warning and error messages that are important to look at. And then some commands will actually output useful things like the group command prints the number of atoms in the group to the log file, and the delete atoms command prints how many atoms were deleted. There's some pre-run info. This is like statistics on the neighbor list, how much memory you're using, and then you get these columns of thermodynamic output every n steps. That's like the current state of the simulation at that time step. The thermostyle command defines what is actually output. So if you go back, it was like the temperature and the white dim. So you can use that to, just look and make sure your simulation is blowing up, or you can actually plot that, just to see if things are reasonable. And then you get the post-run info. So this includes some CPU timing, like how long did it take to run the simulation, a breakdown of where your time was spent in like the computing forces versus the neighbor list versus communication. So you can look at that and see if there's any performance issues like big load imbalance, or one category taking an inordinate amount of time. And then there's also some stats on atoms and neighbors on the counts and the timings for those as well. For the dump file, it's one snapshot of per atom info every n steps. So you can't actually put per atom quantities in the log file. They have to go in the dump file. So the dump file is per atom, so one quantity for every atom. There's different file formats depending on which style. If it's text, binary, or you can even dump an image or a movie. The input script you can have multiple dump commands. You can choose which atoms. So you can only dump, one group or another. There's many ways to get per atom output. So it includes some fixes, computes, and variables will dump per atom values. You can also output per pair and per bond info to a dump file. And this is really useful for post-processing if you want to visualize your simulation. Okay, and then there's also some other commands, fixed commands, that do time averaging and compute and can produce output files. So there's like a fixed app time, which can output either scalar or vector quantities. You can create a histogram, and you can also produce correlation coefficients for scalars and vectors. Okay, so here's some tips for writing and debugging an input script in LAMMPS. So it's really this similar to writing any computer program. You want to start as simple as possible, and just slowly add complexity one command at a time. You can look at the log file, plot the data. Is your pressure blowing up? Are you getting bands in the output? You can even visualize it at every stage. There's two kinds of errors. So there's syntax and runtime. Syntax is like you type the command wrong, like actually showed in the GUI. The GUI will actually highlight which line has the wrong syntax. And then for syntax errors, one common thing is that you try to use a pair style like maybe EAM, but you haven't built with the needed package. So you haven't built with the mini body package. The LAMMPS will tell you, pair EAM is part of the mini body package, which is installed in this version of LAMMPS. If the error is not obvious, you may have to go back to the documentation and look at the doc page for that command. One thing to note is that the website, so if you go to lamps.org and go to the manual from there, the website is only for the current feature release. So if you're using some older version, like a stable version, then you're going to have to go and look at the documentation for that version, because the website is only the current release. You need to pay attention to any warning messages, because those are really helpful. We try to make those as helpful as possible. Okay, so that was a syntax there. Now, how do you debug runtime errors? Well, these are harder. Some tips are to look at the pre-run portion of the log file, make sure everything is well, make sure that it's doing what you expect. You can also add print commands with variables to examine values, and put out for those to the log file. Another thing you can do is run every thermal output every time step, and you can see exactly where you're getting this error on what time step. It's helpful to run a small problem before a big problem, because small problems are easier to debug, easier to visualize, easier to understand. Run in serial before you run in parallel, and then you can plot the thermal output as well as visualize snapshots to make sure that everything is doing what you think it should do. There's 4 flavors of runtime errors. Some are easy, some are hard. The easiest is if it just triggers an error message like out of range atoms. And the cause is normally either overlapping atoms or you might have typed in your model parameters wrong and something's blowing up and LAMMPS will tell you it lost atoms. A little bit harder to debug is when you see the thermodynamics blowing up, so you get, ridiculously high energy or pressure, or maybe even it throws an infinity or a nan, not a number. So again, that could be a bad model, or maybe your time step is too large, and you just need to check your time integration parameters. The third hardest is if your simulation crashes with no error message or blow up. If the thermodynamic output looks good, like you're not getting infinity, then it can be helpful to report it. You can report it on the mat side form. And if the answer is wrong, but the simulation runs and everything looks fine, that's the hardest to debug. So first of all, how do you know if it's right or wrong? Maybe it's just normal statistical variation. LAMMPS could be doing what you asked, but your model is wrong. It could be a bug or a problem with LAMMPS. That's not super common, but not impossible as well. So this is really hard to debug without some knowledge of molecular dynamics. So if all else fails, you can ask a local LAMMPS or MD expert, such as your advisor. You can post a message to the discussion forum, so that would be the mat side forum. You can see the link and sign up for that. You can see the website for more details. So that's all I have.
Oh, perfect timing. Okay, so next round of demonstration. We find what to show. Okay, so we're in the next folder. So one important difference between the text mode and the GUI is that there are no arguments or flags to the GUI. You just give the file name directly. So we have another input. It's another 2D system, and in this case, it's the flow around some obstacle particle. And again, let's have a look at what it looks like. So that's the initial configuration. We have a bunch of atoms, and we have applied forces, and there's a fixed add force that adds a force in the horizontal direction that will make the particles flow. And specifically, there's this wall that will repel the particles, so they will have to flow around it. And then where the blue atoms are, this can move. So there's a fixed aver force, which will take the force on it and average it, so that the entire block gets the average force, and it will kind of adjust to the pressure that is in the flow around the obstacle. And you can see this in the input. We have here, so here is where the obstacle is defined through a region. Region void, this is where the atoms are deleted. And then we're putting a wall around this region that is harmonic repulsion that will repel the atoms so they won't go into this void. So we're creating a velocity. We're doing a regular time integration. The lower atoms are just set at rest, and the upper atoms are set to non-experienced forces in X and Z, but in Y they're free, and that's where we use the aver force fit. fix to basically adjust the pressure on the lid, so to speak, on the system. And then here we are using the flow, and to make this a dynamical equilibrium, we're also applying viscosity. So the add force will push the atoms, and then the fixed viscous will dissipate the energy. So that there should be the interplay between those two will make a difference. So this is what it looks like when you just run it with the given parameters. And one thing that you would want to do is to vary these parameters, and that's easily done with variables. So you can do different runs where you set the variables to different values. And that's essentially the first task that is given here. And we have we're supposed to add three variables, one that is push, one that is called damp, and one that is called compress. And we're turning this into index style variables. So now you see here's already the completion variable is the selected completion. I can just go there. So we do push, and then we have index, and again, completion will give us the choices of possible values. Now we're doing again variable. What's the second damp? Index, that was half, and variable compress index minus 1/2, if I'm not mistaken. So now I'll save this. And now I have to apply the changes here in the various fixes. So this would become, so when the input is being processed, $compress will be replaced with the value of the variable compress. And the benefit of index style variables is that you can change them from the outside, and then the definition in the input file will be ignored. So other variables like equal style will be reset whenever the variable is redefined. Index style variables will be kept at the first set value. And that allows to change them from the outside. So that would be push. And here we have damp. So we also see there's an attempt to do completion for variables. So I can now run this. And since I use the exact same values as before, the simulation looks the same way. And we can look at that's the output. So we wouldn't see anything here now, but I can go to the preferences, and we can tell LAMMPS to echo the input commands also to the output buffer. So if I make this change and then run again, and look at the log file. And you can now see how it processes this. So you see fix upper ever force $compress. And then the next line is the one with the variable substitution. And the same for push and damp. Now, with the GUI, we can actually, we have to restart. So let me do this. And now, when I reread the input, the GUI will actually check for any variable settings. And now I can, for example, increase the damping and maybe also increase the compression and increase the push force. And this will now be applied in the same way as you can apply it to the command line. And now we see that the behavior of the system is slightly different due to, so it's moving faster and the pressure response is different. And we can now check this, change this wherever we want, make it slower, for example, and run again. Now you see there's less energy pushing the atoms forward. We can also do this from the command line if we have this, we can do push and this will now run this without the benefits of the GUI, but it will still apply the change variable from the command line. So you can do series of calculations where you just change parameters in the input to the command line. So let's have a look. What's the next task? We can use some other region command. Can change the size, but we can also change the shape. So let's, for example, instead of a sphere, let's use a block, and that would go from say 7.99 to 12.01. Quick. And now we see that the shape of the obstacle has changed from a sphere to a rectangular block. Let's see what else is in here. There's the size. So a fancy thing that's not in there that we can try is we can also try to rotate this. For that, we have to define a variable. take this. So the important point here is that I'm referencing the variable not with the dollar, but with v underscore. That's a special case. That's when the command knows how to deal with variables. Whenever I use the dollar, it is handled at the pre-processing stage. So it uses the value once the line is read and processed, and it cannot be updated. Whereas when I use a v underscore variable reference, then the command has to be able to handle variables, but it will then evaluate the variable during the run. So you can also make this dynamic. The moment I'll just make it static. And we need to have a center that would be 10, 4, 0, and would rotate 0, 0, 1. See if I got this right. Always a bit risky if you're not looking at the manual while you're doing this. Yep. Time to make zeros. So now you see I've rotated the region. And let's see. Now, if I'm really lucky, I can make this dependent on the step variable and just make it go very, very slowly with the step and rotate. Was maybe a little bit too close, too slow. So you see now the variables being evaluated at every step, and the obstacle is rotating. And I think that's more or less what I have for this section. And again, this of course works the same way for the command line as it works for the GUI. But you see with the GUI, a lot of the steps get more easy. If I need to look up the manual, it's just one command. And you also see once you know the hotkeys, it's very convenient to just go through this. So I even though I don't usually need a beginner level introduction to LAMMPS, I use the GUI because it's for simple inputs. It's just so much faster to debug stuff because everything is just within the same executable, and you can just run hotkeys to make a change, rerun. You don't need to save anything. You don't need to switch to a console and another editor and another window. It's all the same thing. And you can set up the visualization to immediately show you what you see. You get the plots of the energies right away. So this makes things rather convenient. You ready for more, Stan? Okay.
Okay, now we're going to talk about styles and lamps. So the goal for this lecture is to teach you what styles mean. We're going to look at some of the most virtual styles and what they do, and how styles let you tailor your own lamp simulation. And if you are able to familiarize yourself with styles, you'll know a great deal of what lamps can do for you. Okay, so what is a style? A style is a command with many variants. So we talked about a pair style. We also talked about fixes. So examples of pair styles are pair style LJ cut, EAM, etc. Fixes could be NVE, bridges small, etc. So you may be looking at these, commands and wondering, why is it a pair style but not a fixed style? So if you can only have one instance in your entire LAMMPS simulation, then it includes the name style. So you can only have one pair style, but you can have many fixes. So the style has a virtual parent class with many derived child classes. So the parent is pair.cpp or fix.cpp, and then it has several children like pair LJ-cut or pair EAM, or fix NVE and fix rigid small.cpp. So all of these children are derived from the parent pair.cpp or fix.cpp. There's about 20 different styles in current LAMPS. Most are invoked in the input script, but some are just used by LAMPS internally. And if there's an asterisk, it means you can only have a single instance of that style at a time. So we're going to look at the ones in red: pair style, bond style, cage-based, fix, and compute. You can see what the different pair styles do. So for example, we have 275 different pair styles. So that means in LAMPS, there's 275 different models to compute your forces. And then, many fixes and computes as well. So we're not going to talk about all the other styles, but just be aware that those are options in LAMPS. Okay, so let's talk about pair styles. This is really LAMPS lingo for interatomic potentials, also known as force fields. So it defines how atoms interact with each other, how you compute the forces. Pair styles are only the short range part. We'll talk about case-based styles in a moment, which are the long range part. So this is a critical choice for your model and your material. So looking in the literature could be helpful, but you have to make sure that your pair style can include the physics that you want. So for example, if you want to model a semiconductor, then using a pair style for a metal is not a good choice. That's not going to have the physics that you need. There are also trade-offs in accuracy versus computational cost. So there's some really expensive machine learning potentials in LAMPS. So you may or may not need that much accuracy. They're very expensive. A pair style can be either pairwise or mini-body. So even though it's called a pair style, it can be mini-body. So some examples of pairwise are Leonard-Jones, Coulombic, Buckingham, etc. Mini bodies include EAM, Tursoff, Rebo, and ReaxFF, as well as some expensive machine learning potentials. You can include the short range part of Coulombics, but not the long range part. That could include LJ-cut cool cut or LJ-cut cool long. This is really done to optimize the inner loop. So here's some categories of different pair styles. So if you want to model a solid, like a metal, then EAM is a good choice. There's also others. For bio and polymers, then you could use charm force field or others. For reactive or bond order, there's the mini body Tursoff potential, and Rebo, Comb, Reax, which is the reacting force field, etc. There's pair styles for coarse grain simulations like dissipative particle dynamics or granular. And then you can even have non-spherical interactions with like a Gabor ellipsoid or other more exotic potentials in LAMPS, like triangles. You can also tabulate any pairwise interaction. So if you have some potential, but it doesn't fit the functional form, but it's pairwise, you can just put it into a table. There's also pair hybrid, which allows you to have multiple pair styles. So this could, for example, allow you to model a polymer on a metal. And so you have one pair style for the polymer, one pair style for the metal, and then some way to do the cross interactions as well. It could also be used for carbon nanotubes in water, or say a solid interface between two different materials. and you use two different peristyles for the different solid materials. So you can see a list of all the peristyles available in LAMPS through the documentation. On the command part of the website, there's a section for peristyles. They're annotated with certain letters, so GIKOT for the different accelerated variants, which we'll talk about in a moment. So G is for the GPU package, I is for the Intel package, K is for the Cocos package, and then there's the opt and the OpenMP. And there's also PairKim, which is the interface to the OpenKim repository, which has a whole bunch of, many more peristyles that you can also tap into through OpenKim. So there's one-line descriptions of peristyles. You can see the peristyle doc page. So for example, we'll just pick one. You can look at Beck, which is the Beck potential. BOP is the bond order potential. So this is just like if you're looking through and I don't know what this means, what is pair ETM, you can see this one-line description in the docs. Okay, so here's the relative CPU cost at different potentials. It can be very dramatic. So in this table, everything here you can see the LJ ratio. So Lennard-Jones is obviously 1. So a granular and a bead spring peristyle is less expensive than Lennard-Jones. So you can see this is the system, this is what it's used for, and how much memory it took. So these are very lightweight, cheap, computationally cheap potentials. And then the peristyles after are more expensive. So EAM is about 2.3x more expensive than Lennard-Jones. Tursop is about 5 times more expensive, but you're getting a lot more physics, so there's a trade-off between computational cost and accuracy. And then there's some even more complex. So Reacts FF is a reacting force field is over 100 times more expensive than Lennard-Jones. And then not shown here, but there's like machine learning potentials like SNAP or ACE are thousands or more X more expensive than Lennard-Jones. But again, Lennard-Jones is very simple. Maybe you could model a noble gas like argon, but not a metal or a reacting system. You need something more expensive. You can also see the benchmark website has more details and some plots. Okay, so we talked about peristyles. Now we're going to talk about bond styles. And there's also the same thing for angle, improper, dihedral. So this is LAMMPS lingo for intermolecular 2, 3, or 4 body interactions. So this is a fixed covalent bond. If you want to break and form bonds, there's another fix called fixed bond react in the reaction package. So if you want to, you need a bond style, but you don't know which one, where do you go? Hopefully, by now, you go to the commands, you click on bond styles, and then you can get this one-line description of different bond styles. So for example, harmonic is a harmonic bond, shifted harmonic bond for harmonic shift. So each one of these bond styles have its own documentation, and you can click on that and learn more. Okay, case-based styles. This is LAMMPS lingo for long-range Coulombic solvers. You can see the website commands case-based style. There's 3 different methods in LAMMPS. There's the traditional Ewald sum, which scales as order into 3 halves, ideally. There's P3M, which is like particle mesh Ewald that you see in other electrodynamics codes. That scales as order in log n. And there's also a multi-summation method, which scales as n. So, typically you're going to use P3M, but there are some other additional options. For non-periodic boundaries, you can use P3M for the non-periodic C. MSM, you can use non-periodic in all 3 dimensions. There's also options for long-range dispersion. So like it's basically an infinite cutoff for Lennard-Jones, as well as dipoles. So as I said, P3 is typically the fastest for most systems. If you're, have a really huge simulation, then the FETs may not scale well at large processor counts. MSM can be faster if you're running low accuracy or very large processor counts. Another thing that you need to pay attention to when you're using a K-space style is the cutoff and the accuracy. So this is shifting, so you can shift work between real space and K-space, reciprocal space. And that can really affect performance. So maybe, you want to run, if you want to shift more into the real space, if you have a lot of compute power, otherwise maybe you want to shift more into K-space. Okay, we talked about fixes. This is the most flexible feature in LAMMPS. It controls what happens when in a time step. There's different times when the fixes can be invoked. So here's a typical ND loop over time steps. You're going to communicate ghost atoms, build the neighbor list once in a while, compute forces, communicate more data, and then output. You can have fixes interspersed in this loop. So some initial fixes are like time integrators. So if you do initial integrate for the relay leapfrog, thermostats, varostats, neighbor fixes are like inserting or deleting particles, and then force fixes are like constraints like Longevon, thermostat, a wall, spring, or gravity. And then you also have the final part of the time integrator, as well as some in fixes, which is like a temperature rescaling or diagnostics. So as we said previously, each fix takes a unique alphanumeric ID. So you can call that whatever you want. It's just your personal name for that fix. And then you also have to choose what group of atoms to apply the fix to. So that could be just all atoms, or it could be a smaller subset. So in the obstacle script that Axel just showed, here are some examples of the groups. So all atoms are being time integrated, but only the flow atoms are being rescaled with this the temperature rescaling. The upper part has this one add force fix, and the flow has another add force fix. Move the particles. So in any input script, you could have dozens of different fixes. You can use the same fix multiple times or on different groups of atoms. Fixes can also produce output and store per atom info, which you could put into a dump file. Some examples are like the thermostat energy, forces on the wall, and you can use those in other commands or variables or dump to the logger output files. So again, where you go to commands, fix styles, and then find that fix and click on the doc page, and that will tell you information about that specific fix. Okay, and finally, compute styles. So LAMMPS lingo for a diagnostic computation. So they're calculating some property of the system. It's always for the current time step. And one really important thing to know is that if you define a compute, it doesn't invoke it. So other fixes or output commands are the only things that invoke computes. Like if you have some thermal output or a dump file, then that will actually go and call the compute, and only when needed. So some examples are like a thermostat, like a temperature compute temp. So again, you have to use this in either the log file thermal command or in some other file or fix. There's also time averaging fixes such as fix at time, fix at chunk, which is like a binning or a spatial averaging, and fix at atom, which is averaging over per atom data, as well as at histo, which is for histograms. You can write thermal output to the log file, so that would be like compute temp produces a scalar, PE is the potential energy or the pressure. And then there's also fixes or computes that You can write to the dump file, so these produce per atom data, like the compute cord atom, CNA atom, or the Voronoi tessellation. So all compute store output. It can be global per atom or local. Computes with /atom suffix produce per atom info, and with /local suffix produce local info. Scalar versus vector versus array data structure. So, some fixes may produce only one value as a scalar, others produce multiple or even an array of values. Computes. These are accessible by other commands or variables, or you can dump them to the log file or a dump file. So some examples are temperature and pressure. That's a global, like temperature is a global scalar, pressure is a vector. The potential energy of each atom is per atom vector, so you could use that in a dump file. Displace atom is the displacement. That's also per atom array. So you have, each atom would have XYZ displacement. And then there's also per local, bond local, or local per neighbor or per bond info. And again, go to the doc page, look at commands, find the compute styles, and then find that specific doc page for the compute that you're interested in. So that's all I have.
So it's me again. Okay, so for the last demonstration, we want to look at computing some properties. So let me start again the LAMMPS GUI with the example input here. So this is rather simple Leonard Jones liquid with thermalization. So if we run this, we see atoms just diffusing around. So that's it's pretty straightforward. You read through the README file, it will tell you that if we change the rho parameter, we can change the density. So make it more gas-like. But this one, I will still be behaving like a liquid, or increase the density. Again, I'll just set the variables externally. So let's go over 1. And now we see that's essentially solid. There's some stacking faults, but the system remains solid. So of course, now the question is, we can see this qualitatively. Can we quantify this? And one simple thing to use a property is a radial distribution function, G of R. So now we're effectively supposed to add this. So we need to ultimately, effectively, we need to do 3 things. We need a compute that defines the computation of the G of R. We need time averaging, because the G of R is only really meaningful if you average over multiple computations for a given time. And then we need to output this and convert this to a plot. So I'm gonna cheat. I have the commands that I need right here. Let's copy them and insert them here. So to explain, so we're defining the compute here, and we're telling on top of just normally the computer here will use the pair style neighbor list, and thus you can only compute the because it uses the neighbor list to find the pairs of atoms for the histogram. So you can only do it up to the cutoff. If you want the structure computed beyond, you have to provide an extra cutoff so that it creates a new neighbor list that would extend to the desired cutoff. So this is 50 sigma, that's very, very far out. Then here we have the time averaging. So here, these three numbers are the relevant numbers for the output. So we're computing, we're using the data every 10 time steps. The G of R is strongly correlated. There's no point to accumulate it more often. And we output it every 25,000, and we're averaging over 2,500. So we're basically averaging over every G of R computation that is done at every 10th time step. So with C my RDF, we're referencing the compute. And we have here a little bit of syntactical sugar. So LAMMPS has over the years been trained. If you have a compute that produces multiple outputs, that it can expand this, so you can just give it a star instead of specifying them individually. And then the LAMMPS input parser will expand this. So in this case, there would actually be three outputs from the G of R compute: the distance, the G of R itself, and the integrate over R from 0 to R over the G of R, which is effectively the number of atoms up to that point that are coordinated around this point. We can output this to a file, and in this case, we're output this into a YAML file. So the YAML output format was automatically chosen if the file ends in .yml or .yaml. That's also not supported by all commands, but the commands that do make it easier to post-process this, because you can then dump the entire input and read it into Python without writing an extra parser, because it will be read into dictionaries with the PyYAML module in Python directly. And we have to tell it mode vector. That means that each property is not a single property, but a sequence of properties, a sequence of numbers. But that's what the RDF does. This is often needed for certain computes because they can provide different types of output. And so the time averaging needs to know what kind of output is there. Then the fix modify command that is following here, I actually need to change it. It's the same line, fine. This will change the column labels of the YAML file. So normally it would be C underscore my RDF1, C underscore my RDF2, C underscore my RDF3, which doesn't tell us much. Since we know what it is, we can actually tell LAMMPS to modify the title string that it outputs to custom string. So we are outputting R, G of R, and integral over R of G of R. That makes it easier then to process this. So let me just go back to the original setting that we had, which I think was 0.7, and run the simulation again. So now the simulation is running. Same thing happens, but it should, in addition, produce this YAML file. Okay, so let's have a look. And indeed, we have the file here, RDF. It helps if you type correctly. And so we see now there's the list of column titles, just as I put them in the input file, and the data organized by timestamps. So there's, in this case, there's just one data frame because we're running 25,000 steps and we're outputting every 25,000 steps. And now we need the virtual environment with matplotlib and pandas because there is this plot RDF script, which is here up to this point. It's just boilerplate code for reading YAML data. We're reading the file rdf.yaml with the YAML importer in Python. And now we have in keys the dictionary of the keywords that are stored in the YAML file. And here with this loop, we're converting the individual data sections into pandas data frames and combine them. In this case, it doesn't make a big difference because there's only one data frame. But once we have this, we can then very quickly generate a plot through all the built-in functionality of pandas and matplotlib to get this output. So if I just run and hope I'm not embarrassed by my own scripting. And we'll run for a bit. And we have now, oops. A plot that is showing us the G of R for this given configuration, which is quite typical for liquid where you have a soft peak following. So we can look how this is different if we're running again with the solid. So let's go back to 1.2. The interesting thing here is really, if you set it up like this, you don't really have to do any LAMMPS specific programming. You just output files that are in standard formats, and you can use standard tools to post-process them. And now we see this is quite typical radiation distribution function for a solid, where you have more pronounced peaks and zero areas, zero density areas in between. Okay, so I think the next task is to do mean square displacement, if I'm not mistaken. So let's take this and comment this out. And have here so in principle, what happens here is almost the same. We're computing the mean square displacement, where it creates an internal reference of the initial state, and then computes the square distance. And this is averaged over all particles in the group, so in this case, over all atoms. And then you can use that information to compute the self-diffusion coefficient. And in this case, the result is just added to the thermal output. So we'll just run this. Yeah, so I can now switch this to this value here. And we see it's already adjusting to some values at this point where we get 0.80, around 0.88. So if we now switch to make this liquid, it should be much higher. And indeed, this is the temperature. So now this one's moving out. So in the first case where there was actually no real movement, it was constant, and now we get the diffusion coefficient, and you can make this a bit more effective. The problem with using the mean square displacement is that it's still a very noisy property. So you can actually store the last n values in a vector and then do a fit to these last n values. So rule of the thumb is that you use like the last third of the graph and do a linear fit to this. And that's about the most accurate way that you can compute this, the mean square, the self-diffusion from mean square displacement. In the answers file, there should be an example where this is shown. Well, actually, this can be done. So here you have this fixed vector. So vector will store values. So it will compute the mean square displacement, put it in the vector, and then grow the vector. But this one has a maximum of 1,000 entries. So after 1,000 entries, it will just cycle them around. So drop the old ones and put in new ones. And this way you have basically a chunk of the most recent MSD values, and then you can use the slope function to do a fit to these 1,000 vector points that you have collected from the 20,000 or so individual data points. Another thing that is here, so this has to change the rho value to 1, and then do a modification to the dump image, where we now compute the coordination number of each atom and use that property to colorize the atoms. Oops. Actually, so need to comment out the other dump. First, the GUI can only recognize one dump. If you have two dumps, it will just be confused. And now we see in the animation that it has computed the neighbors and colored the atoms according to the neighbors. So that was now for one property. If we change the rho value, this was for a half. We change it to 1. We'll now see that specifically at those grain boundaries, the atoms have different numbers of neighbors, and inside the solid areas, they're constant. So you can, since we have also per atom variables, you can use this mechanism to do rather complex processing. You can modify in the visualization both the color and the diameter of objects, and so you can do rather fancy things and do this on the fly. And in this case, you can even see it as it is happening. So for debugging, it's pretty straightforward. We have an example about viscosity, but I think this is a little bit over the top. So I think we stop here now. And somebody has more ideas. There's like the tutorial files have all the questions and answers. There's also, there's no reason to show the viscosity thing from the GUI because everything is computed. So that's one of the things where the GUI doesn't help you. Unless somebody, I've been thinking if somebody really has time and the energy, I would be cool to have sort of these wizard dialogues where a beginner user can say, I want to do the RDF calculation, I want to do the MSD calculation, I want to do a viscosity calculation. And then you define the properties, the settings, and then the wizard will compile the necessary commands for you into that. But that's a lot of work. And viscosity and thermal conductivity and all of that is not my personal expertise. So I don't want to put something out there that will give people wrong results. So what's the next one? Was it accelerators?
Accelerator.
Okay, yeah, so let's do that. You want to do the other talk too? Sure. Okay, so let me stop the sharing.
Okay, now I'm going to talk about accelerator packages and lamps and also performance. Okay, so here's some motivation. Currently 9 out of the top 10 supercomputers use GPUs or graphical processing units, according to the June 2024 top 100 list. All 3 US exascale machines will also have GPUs. So that is Frontier at Oak Ridge, Aurora at Argonne, and Capitan at Lawrence Livermore National Lab. So Frontier will have AMD GPUs, Aurora will have Intel GPUs, and Capitan will have AMD GPUs. And Frontier and Aurora have both broken the exascale or exaflop barrier, which is pretty cool. So to run on GPUs, you need special code. So you're just regular C++ with MPI won't allow you to take the full advantage of a GPU. And then you can also use multi-threading on mini-core CPUs as well. Okay, so there's different accelerator packages and lamps. So an accelerator package is just really like a different version of lamps that supports a certain type of hardware. So there's the vanilla C++ version, so that's just regular C++ plus MPI, and that will not run on GPUs. Then you have several different accelerator packages. So the first is the opt package. That's just some parastyles. It's again C++, but it has some optimizations that may run faster on CPU hardware. There's also the OpenMP package written by Axel. This is native OpenMP threading, so you can run multiple threads via the mini-core CPU. There's the Intel package. So this is similar to the OpenMP package, but it also has enhanced SIMD vectorization. It's fast, very fast, not only on Intel CPUs, but pretty much all CPUs. But it's also very complex code. There's the GPU package, which has native CUDA, which is the NVIDIA vendor library, as well as OpenCL support. And then there's also the Cocos package, which can run on GPUs as well. And so the difference between the GPU package and the Cocos package is that the GPU package only runs a few kernels, like the force pair calculation and the neighborless build on the GPU, and everything else runs on the CPU. So you really need multiple MPI ranks per GPU to parallelize what's running on the CPU. In contrast, the Cocos package tries to run everything on the GPU using the Cocos Performance Portability Library, and it supports NVIDIA, AMD, and Intel GPUs using different backends as well as multi-threading with OpenMP. So I'm going to talk a little bit more about these each in detail. Okay, so first the opt package. Again, this is some optimized versions of certain hairstyles. So you need to first build lamps with this opt package. So all of these accelerator packages are optional, and you have to enable them at compile time in order to use them. And then if you want to run with 8 MPI, you're going to invoke lamps with 8 ranks. This is the input script, and then this minus sf opt is the suffix command. What this does is it automatically appends this opt suffix onto anything it can. So if your peristyle supports opt, it will run with opt. If a fix or compute doesn't support opt, it will just fall back to the regular version of, or the regular vanilla C++ version of LAMMPS. So for example, you have LJ cut, and you use this suffix command minus sf opt, then it becomes peristyle with LJ cut opt, and you don't have to change the input file and manually put in /opt on every single style. You just use this suffix command instead. Okay, the OpenMP package. So it has some documentation page here. It uses the OpenMP library to enable multi-threading on CPUs. So you may think, that's great, but keep in mind that normally just using MPI parallelization in LAMMPS is almost always faster than using multi-threading on CPUs. If you're running many MPI ranks across multiple nodes, then you can get up to a communication bottleneck. So using MPI with multi-threading OpenMP could be faster. The larger the job, the more nodes you have, the more cores per node, the larger the benefit could be. OpenMP also has some optimizations to vectorize better. So this is SIMD vectorization than the vanilla LAMP styles. It also has some other optimizations like in opt, which reduce some overheads of if statements through templates. So again, you have to compile LAMPS with the OpenMP package. So if you're either using CMake or traditional make, you have to enable this OpenMP package. And then, for example, if you want to run with 2 MPI ranks and 2 OpenMP threads, then you're going to set OMP num threads to 2, launch with 2 MPI ranks, and then include this suffix command minus sf OMP, and then it will automatically enable any of these optimized styles that are in your input script. Similarly, for the Intel package, again, it allows code to vectorize and run well. So you could get, up to 2, maybe even 4x speed up over just the regular CPU code in some cases. It also supports OpenMP threading. You can use it combined with the OpenMP package. So it's normally the best performance. So if your peristyle supports the Intel package and you're running on a CPU, then you should use the Intel package. Unfortunately, not all styles are ported to Intel, and if that's the case, then you won't get any speed up. One nice feature of the Intel package as well is that it supports reduced precision. So mixed FP64 or this double precision, and FP32 is single precision, or you can just run in pure single FP32. So There's trade-offs, with reduced precision, you get worse energy conservation. So you just have to know if your model can handle using reduced precision. The mixed precision is more accurate, so you get almost the speed of single precision, but almost the accuracy of double precision. So to run the Intel package, again, compile, enable this optional accelerator package, and then there's a few more options. So you're going to run with 2 MPI ranks. This is the input script, and here's the suffix, here's the suffix command, but then there's an additional package command. So this -pk is described here in the docs. -pk Intel just says which package, and then these are some options. This is saying use 2 OpenMP threads and then double precision for the calculations. And these are all described in the package document doc page. For the GPU package, again, this is designed for 1 or more GPUs coupled to mini CPU cores. Only the peristyle runs in the GPU. The time integrator, and any other fixes or bonds or computes all run on the CPU. This means that the atom-based data, like the coordinates and the forces, have to move back and forth between the CPU and the GPU every time step, which can have some overhead. You can overlap some computations. So you can actually overlap the short-range peristyle with the long-range K-space, like P3M. The GPU package uses NVIDIA CUDA for NVIDIA GPUs. It supports HIP for AMD GPUs, and it also has more general OpenCL support. Just like the Intel package, the GPU package also supports reduced precision, either mixed or pure single. So running the GPU package is a little bit more complex. First, you have to compile the GPU library. If you're using the traditional makefile, I believe with CMake it is automatically enabled and the library is built. And then you need to enable this optional GPU package before you compile. And then if you want to run, say with 16 MPI and 4 GPUs, so that would be 4 MPI per GPU. This is 16 ranks, your executable input script. Here's a suffix command for the GPU package, and then here's a package command. So this is saying use 4 GPUs per node, and then that would be 4 MPI ranks per GPU. One thing to remember if you're running on NVIDIA GPUs is to use CUDA MPS, the multi-process service. Especially with newer NVIDIA GPUs, this will really help performance by not serializing some things between MPI ranks. You'll automatically overlap peristyle on the GPU with K-space on the CPU, which is a nice feature if you have K-space enabled. Okay, and finally the Cocos package. So this is Cocos library is used in many codes, not just LAMMPS. It's an abstraction layer between the program and next generation platforms. And what Cocos allows is the same C++ code to run on multiple hardware, so different kinds of GPUs as well as CPUs. The way that this works is really 2 main parts. The first is parallel dispatch. So you take like a loop over atoms, and you map that onto backend languages like CUDA or OpenMP. And then the other part of Cocos are Cocos views. These are multi-dimensional arrays that can be optimized for a specific hardware at compile time. Cocos is used on top of MPI. It's open source. You can see the Cocos documentation for more information. So we've taken this Cocos library and we've implemented it into LAMMPS. So in order to run Cocos, you need a C++70 compiler. So that's a newer, not ancient compiler. It supports both OpenMP multi-threading as well as GPUs. Again, it's designed so that everything, all the peristyles, fixes, computes, run on the GPU with minimal data transfer between GPU and CPU. So there's a relative performance penalty if something isn't ported to COCOS because then it has to run in serial on the CPU. So, you just need to make sure that the model that you're using, all the parastyles and fixes are ported to COCOS for optimal performance. It only supports double precision. And so here's an example. So again, the package command toggles certain options like a full versus half neighbor list, Newton on off. And you can set those on the command line using this package command along with the suffix command for COCOS. So here's an example. Again, compile with the COCOS package. It's optional. Run 4 MPI ranks and 4 GPUs. So here's the number of MPI ranks, executable, input script. And then this is additional with COCOS. You need to turn on COCOS. So -K on is like COCOS on. This is the number of GPUs per node. So 4 GPUs per node. Then here's a suffix command. If you want to run with OpenMP threading, then it's similar, except instead of G4 for GPUs, you're going to use T4 for threads. Okay, some things to keep in mind to get good performance is affinity, which is how you're binding your tasks to the available hardware, the nodes and cores. So for MPI, you can use different command-like arguments like bind to core or bind to socket. You can also use these OpenMP variables such as OMP proc bind and OMP places. And then one more thing you need to pay attention to if you're running on a GPU system are NUMA bindings. So for example, if you have a dual socket system, then you need to make sure that the MPI tasks driving the GPUs are on the same socket as the GPU. Otherwise, you'll have an additional overhead of going across the socket or between two sockets. Okay, so how do you know LAMMPS is running well, if it's fast or slow? So one thing you can do is look at the log file output. So at the end of a simulation, you can look at the loop time. So this is the number of seconds it took, the number of processes it ran on, and the number of steps and the number of atoms. You also get some performance output. So it says the number of time steps per second here. And then you also get an MPI breakdown or the timing breakdown of different parts of the run. So this is the force computation, neighbor list building, communication, output like a dump file, and then modify are like the fixes. So you can see in this example, we had a lot of communication, and so that could point to some problem. Maybe I'm not running optimally. So look at the percent total and see where your time is being spent. Just a note for the COCOS package on GPUs, you need to set this environment variable CUDA launch blocking equals 1 to get an accurate timing breakdown. Okay, so let's talk a little bit about performance. In general, MD parallelizes well. The major parts of the time step, like computing forces or building the neighbor list, can all be done parallel through the domain decomposition that LAMMPS uses. There can be a high communication overhead when strong scaling. If you only have a few hundred atoms per processor, then you can have high overheads. It's even worse on GPUs. You need thousands or more realistically, maybe 1 million atoms to saturate the GPU. There's a couple of different terms we use. Strong scaling is holding the system size fixed and increasing the number of processors. So you have the same number of atoms, and you're just using more and more ranks, like more and more cores or GPUs. That's strong scaling. So the number of atoms per processor or GPU decreases. Weak scaling is increasing the system size in proportion to the number of processors. So your number of atoms per processor remains constant, but the total number of atoms grows as you increase the number of cores. So for perfect strong scaling, if you double the number of processors, it cuts the simulation time in half. For perfect weak scaling, if you double the number of processors, then the simulation time stays exactly the same, but your system got bigger. Your system got bigger, but you're using more processors. And in general, it's harder to maintain parallel efficiency when strong scaling because you have less work and you have more overhead. And so the compute time is decreasing, the communication time is either staying the same or increasing. So it's a lot harder to strong scale and keep your parallel efficiency. So if you want more information on the performance of different potentials, you can see several plots in the LAMMPS reference paper. So it's in CPC, so you can use this as a reference. There's also some benchmarking data on the LAMMPS website that you can look at as well. So thank you. We have the next talk too, right?
Yeah, the last one.
Okay.
I don't see any questions in Slack, so.
Okay. So this is the last talk from Steve. We're going to talk about more advanced topics. And this is really a whirlwind. So we're going to do like one slide per feature or even one bullet point per feature. We're going to talk about additional features and where to get more information about them. So we don't really have a lot of time to cover all the details, but you can always look into topics that interest you later. You look in the doc pages.
And we're here.
And yeah, you can ask us too. Okay, so here's some useful input script commands. Each of these has their own doc page. So there's the info command. This prints information about the LAMMPS executable, which can be useful for if you need to post on the form. We might ask you, what version of LAMMPS are you using? There's the include command. So this can include commands from another script. So maybe you have one script and you want to call or include another script without, copy and pasting the entire text. You can just use the include command. There's some conditional commands. So like if, else, and elif. For scripting, you can print. So print messages to the screen. Can contain variables. We talked about this for debugging input scripts. And then you can also use the quit command that forces LAMMPS to exit. You can also loop. So if you want to, run for 100 steps, do something, some computation or diagnostics, and then change something and then loop again. There's different commands. There's the label. So that sets a position in the input script. Next, we'll increment one or more variables. And then you can jump. So you can jump to a label, so you can jump around in your input scripts and use that for looping. There's variables. So variables in LAMMPS input scripts are very powerful and with many uses. So you can do a one-time definition of values that are used in many places. You can even set these from the command line that invokes LAMMPS. So you could use that. So you could, if you have a bash submission script on a supercomputer, you could set variables in your bash loop and those get passed into LAMMPS. There's different styles. Some store strings or numbers or formulas. Variables can produce scalar or vector or even per atom output. These formulas are C-like, so you can have math functions like logic, and or. You can have groups, regions, scalar or per atom inputs. You can use output from other computes, fixes, or other variables. And it can be time-dependent variables or even spatially dependent. And many commands allow you to input, use variables as inputs. The command can invoke a variable internally. For example, it can define a time or a spatially dependent electric field on your simulation. So for example, you could have a cosine or some complex spatially dependent electric field. Now, there's also action commands. And again, these all have their own doc page. You can see the documentation for more information. So an action is like performing simulation. So there's just a standard run command, that's dynamics for molecular dynamics. There's a minimize, which is energy minimization. So that's like, if you have a overlapping system, you want to relax that. You can do a rerun. So that is 0-step runs on snapshots from a dump file. So you can read in a dump file and then rerun your simulation with some different force model or some change in your parameters. There's also multi-replica simulations, parallel tempering, nudge elastic band, parallel replica dynamics, temperature accelerator dynamics, and global or local hyperdynamics. So these are allowing you to do multiple replicas at the same time, and so very useful. Okay, a few more input script commands. You can run multiple simulations from one script. So this would be like partitioning, run in simulations on pprocs split into in partitions. So there's some how-to in the user guide. You can use a shell command. So this will basically give you a bash shell inside your input script. And you can use that to invoke an external program. So this could be used to couple lamps with other codes, or change to different subdirectory, or run some post-processing script, or just basically any shell command. You can also invoke Python from your script. So you can use Python to pass in arguments to a function, return variables and variables. It can even access internal LAMMPS data and can be embedded in the script or in another file. So this is really powerful to allow you to interface with Python in your LAMMPS input scripts. There's many packages. So we talked about accelerator packages. There's currently about 90 packages within the source directory. So this is really optional code that kind of have a common theme. So for example, the mini-body package has many peristyles that are mini-body. Packages are optional, and so you need to compile with these packages enabled. Otherwise, you'll get an error that says LAMMPS isn't, peristyle EAM is part of the mini-body package, which isn't enabled with LAMMPS. Okay, so you can see in the doc page, there's a one-line description of different packages. So for example, the body package are body style particles. It has a doc page here. And another example is A-sphere are aspherical particle methods like triangles or ellipsoids, etc. There's also coarse-grained and meso or continuum scale models. So this is beyond just the typical all-atom model, so that you can increase your length and time scales. So there's really 3 different categories. There's coarse-grained models. So for example, you have coarse-grained DNA model, or dissipative particle dynamics, or other methods of coarse graining. There's mesoscale models. So you have, for example, aspherical particles. So here's some examples of ellipsoids, body and triangles, and different exotic models and lamps. You can also do large particles with the colloid package, rigid bodies, solvents, and nanotubes. And finally, there are continuum scale models. So the ATC package allows you to couple the finite element. Granular is a granular system. Paradynamics is a meshless continuum model for fracture. And then there's smooth particle hydrodynamics and others for liquids and solids. And so here's some more examples. You may not think of this like as molecular dynamics of atoms, bouncing around. So you have continuum methods. You can look at X-ray diffraction. You can do a lattice Boltzmann model, Monte Carlo, coupling to other codes like density functional theory or quantum mechanics. Many machine learned potentials is something recently that's state of the art. Aerodynamics, reaction, so this is like bonds breaking and forming. Rigid bodies, smooth particle hydrodynamics for liquids, magnetic spin dynamics, and Voronoi tessellations around atoms and particles. Okay, so you have LAMMPS. How do you build a complex molecular system? Well, unfortunately, LAMMPS is not magic. It can't just magically assign force field parameters or build molecular systems for you. So how do you do that? So you need a data file. So the data file lists bonds, angles, and force field parameters of your model. Maybe you have a file from a different code like Charm or Amber. So there's some converter programs included in LAMMPS that can convert from different file types. Maybe you could get a force field for Charm off the internet, and then you can use these converter tools to convert that to a LAMMPS data file. There's also some third-party builders which can create LAMMPS inputs. You can see the website for more details. Some are free, some are commercial. For example, D&D Topo Tools, Mold Template, and then Avogadro, PacMol, ATB, and the Enhanced Monte Carlo. So here's some examples to create molecular systems. So Topo Tools, Mold Template, and the Enhanced Monte Carlo. And then again, you can look at the documentation of LAMMPS and see where to download these and look at the documentation for the specific tool. Okay, and finally, load balancing. This can be especially useful for coarse grain systems, or if you have a very spatially varying system. You use the balance command if you just want to do a one-time static balancing, or use the fixed balance for dynamic load balancing. So you could, say load balance every 1,000 time steps if or every, 100,000 if your simulation is rapidly evolving. So here's some examples. So the first snapshot is imbalanced. So the different colors are the different processors. So the squares are the subdomains of the 2D system. So this is processor 1, processor 2. You can see that many processors have no work, and some other processors have all, fully filled with atoms. So you can, one option is the shift style. So you can just adjust the processor dividers. So you can see it's a lot better for, this processor. Before it didn't have any atoms, now it has balanced atoms, but there's still a couple of processors that are unbalanced. And then there's also recursive bisectioning. So this is, the best. All the processors have basically equal work. There's also more advanced options. You can balance just by particle count, as we're doing here. You can also balance on weighted particles or even the time on the processor. You can also do energy minimization. So there's a few different flavors. There's gradient-based minimization. So this is just your standard conjugate gradient. And you can also include bond length constraints like shape. So this is, you're trying to minimize the energy. There's also some dynamic minimization, damp dynamics like quick min and fire. You can also use that for nudge elastic band calculations. If you just want to un-overlap your simulation, there's a peristyle soft. So that's just a very soft command so that when you run dynamics, it won't blow up. The particles won't explode because they're overlapping. There's also fixed NVE limit and viscous, which will help slow down overlap, you have a strong overlap, then you can slow that down and just try to unoverlap, just using the normal run command. And last slide, there's 45 entries in how-to sections. So, if you want to learn how to do something like how do you restart a simulation, or how do you use triclinic simulation boxes, or, there's specific force fields like a SPC water model, different packages, how to use body particles, or even some tutorials, how to use GitHub. There's many entries in this how-to section in the documentation. So this is a really great resource that you can learn more about LAMMPS. That's all I have.
Okay, so, well, so we have now time for some questions. If there's any remarks or comments or things that anybody wants to ask, either here locally or there's questions from the people who are watching this through the YouTube stream, and post them via this workshop Slack. Yeah.
You mentioned for fix every time outputting data to a YAML text file. Is there also support for binary format for the same kind of output?
Not yet. You have to provide a good use case, and so then it can be done. That one's easier. So the other averaging is a bit trickier to convert to YAML. That's why they don't exist. Yeah, for atoms you can always use dump, but for the other time it would have to be input. It would be nice if we could use some standardized format like HDF5 or something. But that's also then the problem of who's going to program this, and HDF5 always brings so much overhead of a large package and library that you have to compile it into.
I'm asking the GROMACS people who have their own format, they're starting with the same project because trying to move away from that format and dependencies.
Yeah. Yeah.
So a question about the index variables.
Yes.
Is there any, when the index variables are reset, is there any indication in the output file of what the original and reset variables are, or is it done
No,
silently?
so index variables are set once.
Okay.
So the only indication is if you use it, if you have the dollar notation, of course, then you see in the log file what it was replaced with.
Okay.
So index variables in the text in the input can be overwritten from the command line, because if you define a variable on the command line with the -v flag, it will be created as an index. If that is used internally, defined as an equal style variable, you get an error because you can only redefine a variable at it's the same style. But for index variables, the special rule applies that they're not overwritten from the input file. So you overwrite them from the command line, but not the other way around. Okay. So the only way to reset an index variable from the input file is to delete it and then redefine it. Okay. Otherwise, if you use equal style, they will be updated to the new definition. Right. But the general rule is if you recreate a variable as a different style, LAMMPS will stop with the help. There's nothing else, then we can stop for lunch break.
One thing is in the multi-replica section, I didn't catch it, but did you mention the LAMMPS using replicas for quantum nuclei? I think is that still supported? Or was it the path-integral molecular dynamics?
Yes, we're actually getting ready for an update with the IPI package by Michele Geriotti and his co-workers. there also is the fixed PIMD, which exists in two different variants. They both work, so IPI works with socket communication. It's actually meant to have all the classical parts in the IPI code and use the attached code as a force engine. So it's actually not meant necessarily for LAMMPS, but rather for ab initio codes. But of course, now with the machine learning potentials that are developed and integrated in LAMMPS becomes more attractive because you can do bigger systems at the cheaper cost. So and then essentially for fixed PIMD, you do a multi-replica, and then each replica is one beat on the path integral scale. Okay. Okay, so thanks for hanging in here. Let me just stop the something.